All right, here we go with part 2 of Unit 3 in class worksheet. And this problem is asking us to circle all the bonds and identify as polar or nonpolar. Now, I'm not going to circle every single bond in this molecule. What I am going to do is talk through each unique bond. And so this is kind of what I would expect you to do on a quiz, is not necessarily circle every single bond in a large molecule like this. If it's a smaller molecule, perhaps, but large one like this, I wouldn't expect you to circle every single bond, but rather circle the unique bonds. So let's see what we're dealing with here. Start on the right hand side here. I have an OH bonded to an H, and I know that bond is polar because oxygen is more electronegative than hydrogen, and so it will pull on those bonding electrons more than hydrogen will, creating an unequal distribution of those electrons, and that is what makes the bond polar. Here I have a CO bond, and that bond is also polar. And I'll kind of draw the little squigglies here, the symbols indicating where the positive charge is going to be, because carbon is less electronegative, and where the partial negative charge is going to be, because oxygen is more electronegative. On this OH bond, it's going to be the partial positive is on the hydrogen, the partial negative is on the oxygen. Now we could draw another CO bond here, but I'm going to leave that out just for the sake of clarity. This is technically another unique bond, but we've already circled one CO bond and talked about that one, called it polar. Here we have a CC bond. This is nonpolar. Anything bonded with itself is nonpolar. Then here I have a CH bond. CH bond is a very common nonpolar bond as well. Down here I have a CS bond, also nonpolar. Very similar electronegativities between C and S, same for C and H. So they pull on the electrons in the bond about equally, which means that there's an equal distribution of those electrons and no partial charges. Alright, we have a CN bond here. This is polar. Nitrogen is more electronegative than carbon, so I'm going to put that partial negative on the nitrogen. I also have an NH bond here. Partial positive on the hydrogen, partial negative on the nitrogen. And I believe that does it for this molecule. Here's another CO bond, but we're not going to circle that one again. Alright, let's move to the next molecule. Uh-oh. I just realized how this printed. Alright, we'll roll with it anyway. Okay, in this molecule here, this is a carbohydrate molecule. Lots of polar bonds. We have that CO bond again. Partial positive on carbon, partial negative on oxygen. I'll go ahead and draw this CO bond. In this type of representation, there's a carbon represented by this, by each of these intersections. So there are 1, 2, 3, 4, 5, 6 carbons in this molecule. It's just one way that we represent carbohydrates. Partial negative on the oxygen, partial positive on the carbon here. We have another OH bond. Partial positive on the hydrogen, partial negative on the oxygen. We have CC bonds, nonpolar. Guess I should put P next to these polar bonds. Nonpolar, and then CH, also nonpolar. Alright, on this molecule, you'll start to see that some redundancy here. A lot of the same bonds over and over again, which is why I gave you that common polar bonds list to memorize. CN is polar. NH is also polar. And CC is going to be nonpolar. And there's a CH over here also, nonpolar. Okay, sorry about this jumbled mess here. On this next molecule, we have a CO again, polar, and an OH, also polar, CH, nonpolar, and CC, nonpolar. All right, moving on to number 8. Identify all the intermolecular forces present in the following. So in this case, I'm giving you a mixture of water and potassium chloride. Because potassium chloride is an ionic compound, it's going to form ions in water. So let's start with the water, though. So just the water interacting with the water. In this case, we're going to have London forces, as we do with everything. We're going to have hydrogen bonding. Water is very good at hydrogen bonding. And that's all there's going to be between water and water. Now, between water and K plus or Cl minus, this is what happens when you put this KCl in water. It's going to ionize into these two. It's going to dissolve into those two ions. This is where we get the ion dipole interaction. All right, next one, CO2. CO2 is, even though there are polar bonds in CO2, it's a nonpolar molecule. Okay, these polar bonds are pulling, the oxygens are pulling with equal force in opposite directions, which is what makes it nonpolar. Therefore, the CO2 is going to only have London forces between the molecules. This molecule here, this is propanol. So I won't rewrite this all out because this is a pure substance. This is just one compound. It's not a mixture like this was up here. We have London forces because that's present in everything. There's a significant nonpolar component to this molecule. We have a polar bond over here, OH and CO. The carbon's connected to the oxygen, that's polar. And the oxygen's connected to the hydrogen, that's also polar. However, there are a lot more nonpolar bonds. So London forces is going to contribute quite a bit to the interactions of this molecule with itself. But since we have that CO and OH, we're going to have hydrogen bonding because of the OH. And then we're going to have dipole-dipole. And that's due to the CO bond. This next molecule, this is an ether functional group. Again, London forces. And since there's no OH or FH or NH, the connection here is C to O to C. So there's no hydrogen bonded to this oxygen. That means there's no hydrogen bonding. So it is only dipole-dipole. This is a polar bond here and a polar bond here. So it's going to generate these dipole-dipole forces. Now you may wonder, well, why is this one dipole-dipole but this one is not? Well, if you think back to the shape of this molecule is linear. In this case, the shape of the molecule is going to be bent. So It's not pulling in opposite directions with equal force because of the shape of this molecule. Now, it's a little bit beyond what we cover in class, but just to give you some context as to why these two are different. That's why. All right, which would you expect to have higher viscosity and why? Remember that viscosity increases with increasing intermolecular forces. So the stronger the interactions are between the molecules, the higher the viscosity. If I'm comparing these two molecules, first I want to look at the mass. Because remember, London forces, which is a significant contributor in large molecules, London forces depend on mass. So I'm going to look at the number of carbons. 1, 2, 3, 4, 5. 5 carbons on this molecule. 1, 2, 3, 4, 5 carbons on this molecule. So they're about equal size. This one has an OH group, which means it can hydrogen bond. And this one also has an OH group, but this one has 2. So it can hydrogen bond even more, which means the strength of the interactions between molecules of this type are stronger or higher than the strength of the interactions between molecules of this type. So this one will have a higher viscosity because it can hydrogen bond more with itself than this one can. The more OHs, the more hydrogen bonding that can take place. Okay. This next one looks like there's a typo here. Should be a 3 there, I think. In any case, we have 1, 2, 3, 4 carbons and an O. This makes an ether group. This one we have 1, 2, 3, 4 carbons with an O and an ether group as well. I think there's something missing. This must have printed funny. I'm actually going to skip over this one because I think there's some error in the printing. I want to say, well, here's what I'll do. I'll draw in some additional CH2 groups. I think this is what I intended to have here. I intended for you to compare a large molecule with a smaller one. They have the same functional group, that ether, which means they both can do dipole-dipole, but this one is larger. So because of the higher molecular weight, it's going to be more viscous. So the reason here for this one, more H bonding, and this has a higher molecular weight. Remember that London forces depend on molecular weight. So if they both have the same functional group, they both can do dipole-dipole, but then the interactions depend on the strength of the London forces. Okay, last problem, number 10. Which would you expect to have lower vapor pressure and why? Remember that vapor pressure increases with decreasing intermolecular forces. That means molecules that don't really want to stick to each other are going to evaporate faster because they don't have as much holding them down into the liquid phase. So I would expect molecules that have stronger intermolecular forces are going to have lower vapor pressure. In this case, this is just hydrocarbons. I need to think about size. There's no special functional groups to look at, so we only have London forces present. Therefore, I'm going to compare these on size. This one is larger, higher molecular weight, therefore it will have lower vapor pressure. It will want to stick to itself more, or it will want to stick with other molecules that are the same as itself, more so than this one will. This one will be more readily able to evaporate. In this case, I've got 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, so similar size, same number of carbons. But here I have an NH group, which means this can hydrogen bond. This is an ether group, which means it only has dipole-dipole. Dipole-dipole is weaker than H bonding, so I'm going to say no H bonding here. So the forces are stronger between these molecules, which means it will have a lower vapor pressure. All right. I know that was really long, but I hope it was helpful. See you next time.